Hello everyone. It is my great pleasure to introduce our guest speaker today, Professor Emmanuel Tremer from the Cornell University. Professor Tremer currently leads the Cornell Database Group. Broadly, his work aims at making data analysis more efficient and more user-friendly, often by leveraging techniques from the AI domain. His papers have been selected for Best of VLDB, Best of Sigmod, and for the ACM Sigmod Research Highlight Award. Professor Tremer received his PhD from EPFL in 2016 and is a recipient of multiple Google Faculty Research Awards. In today's talk, Professor Tremer will present SkinnerDB, which leverages a principled learning by doing approach based on reinforcement learning for query optimization. Welcome, Professor Tremer.
Thanks a lot for the introduction and thanks a lot for the invitation. Very happy to be here. And yes, I'm going to talk a little bit about our SkinnerDB project and several associated papers, mostly the paper at Sigmod 2019. But I'm also going to talk about some ongoing work that has not been published yet. So the main design goal of SkinnerDB is to get away from those simplifying assumptions that traditional database systems make in query planning, in particular assuming uniform data and uncorrelated query predicates. Because if those assumptions are violated, which often happens in practice, then they cannot guarantee to generate optimal query plans anymore, and decisions such as join ordering might be suboptimal. So our goal was to create a system which makes minimal assumptions about data and about queries, while still being able to give some kind of a formal guarantees on having an expected performance that comes to the optimum. Now, the way in which we do that is by an approach that we call intra-query learning, which essentially means that we learn from scratch during the execution of the current query to make near optimal planning decisions when it comes, for instance, to join orders. So we learn during the execution of the current query, and we apply what we learn in order to optimize the remaining execution of that query. And that differs from another popular and very interesting work stream, which we call inter-query learning. There we essentially try to learn something past queries and try to translate that in order to optimize the current query. Now, one drawback of that is that you need upfront some representative training data, while in our case, learning happens only inside of the current query execution, so you don't need any training data beforehand. In order to enable that, we divide the query evaluation process into micro episodes. We will have 10,000s or even hundreds of thousands of micro episodes per second. So we switch very quickly. And at the beginning of each micro episode, we select a join order that we want to try next. Then we execute this join order for a bounded number of steps, which might generate some result fragments that we collect. And at the same time, it gives us some impression, a sample of the quality for that join order. And we can analyze that quality and learn from it in order to make better join order decisions for the remaining episodes of the same query. And query evaluation terminates once we're able to stitch together a complete query result from all the result fragments that we collect across different episodes, potentially generated according to different join orders. So in the SkinnerDB system, we focus in particular on join ordering decisions because that is often the most difficult and perhaps also the most impactful decision made by the query optimizer. Now, this general scenario matches the scenario of reinforcement learning, where we generally have one agent which performs actions on some environment, and from those actions result rewards. Now, the agent wants to maximize the rewards, but initially the agent does not know the reward distribution that is associated with specific actions. And that means that the agent faces a dilemma between being greedy and exploiting actions that seem to work well versus being curious and exploring actions about which little is known, because that gained knowledge might pay off in the future. Now, the area of reinforcement learning has produced a couple of algorithms that optimally balance between those two extremes in order to guarantee that the reward, the expected reward that is achieved over time, is actually near optimal despite of that uncertainty. And we want to leverage those algorithms for the domain of query evaluation. Now, in order to map this general scenario to the specific problem of join ordering or query planning in general, we essentially have SkinnerDB, our database system, as the agent. One action corresponds to trying one join order for one episode. And the environment is characterized by query and data properties. Now, we can define reward as the query evaluation progress per time unit. And then if we optimally balance between exploitation, which means to try seemingly good join orders, and exploration, which means to try new join orders, then we should also get near optimal expected reward. More precisely, we use one specific algorithm from the area of reinforcement learning, and that is the so-called upper confidence bounds on trees, short UCT algorithm. This algorithm represents the space of possible actions by a tree. In our case, this search tree represents the possible join orders for the current query. So one path from the root node to one of the leaf node represents one possible join order. And as the name of the algorithm already suggests, it maintains confidence bounds for the mean of the reward distribution that is associated with different actions. And when deciding which action to try next, it particularly looks at the upper bound of those confidence bounds, which is also referred to in the algorithm name. And then in order to choose a path from the root to one of the leaf nodes, it always selects the child node, which has the maximal upper confidence bound. So in this example, on the first tree level, we would select the leftmost node, which is associated with selecting the table R as first table in the join order. And among the next children, the table S has the maximum upper confidence bound. So we select that as second table in our join order. And now we actually, this is a very small query with only 3 tables. So here the selection for the last table is fixed. And now we have the join order RST selected. Now, you might be wondering, this is a small query, but in general, the space of all possible join orders can actually be quite large. So by this mechanism of always going for the upper confidence bound, the UCT algorithm guarantees that it converges to optimal rewards over time. But you might be wondering whether we don't incur high overheads in creating this tree representing all possible join orders for a given query. However, the UCT algorithm does not build this tree at once, but instead it builds the tree gradually over time and expands it only into the direction of join orders that currently seem interesting. So to make things a little bit more concrete, let's see how the SkinnerDB system builds one of those UCT trees gradually over time by processing a given query. So here we have a visualization for the query 6F from the join order benchmark. So here you see the UCT tree where different nodes represent different tables. And now I'm starting the animation. So we have slowed down the animation significantly. You see how the tree grows over time. At the bottom, you can recognize the average reward associated with specific join orders. The color of the nodes represents the frequency at which those nodes are currently selected. And those green lines, they represent query evaluation progress along specific paths, which means along specific join orders. So once we have a fully connected path drawn in green from the root to one of the leaf nodes. Query processing finishes, and that has happened now. On the left upper corner of the screen, you recognize the number of samples, which is essentially the number of micro episodes. So here, in a little bit over 6,500 micro episodes, we have processed the entire query. Now, this animation is slowed down significantly. In reality, the query processing only takes at most a few seconds for this specific query. All right, so here we have converged to a good join order. Now, in order to make this entire process efficient, we ideally want an execution engine that is tailored to the specific requirements of reinforcement learning. And this is what we are aiming for in SkinnerDB. Now, we have a wish list, so to speak, on our execution engine in order to make this reinforcement intra-query learning approach work well. One first requirement that we have is that when executing a join order only for a few steps, we want to quickly get some kind of unbiased estimates for the quality of that join order, which we can exploit in order to quickly converge to good join orders. The other thing that we want is that because we want to switch quickly between different join orders with a very, very high frequency, we need to make those switches between join orders very efficient. And finally, if for the same query we want to switch back and forth between hundreds or thousands of join orders, then we need to make sure that the execution state we have to keep per join order is fairly minimal, because otherwise we will run out of space. Now, if we consider the traditional query evaluation mechanism, it doesn't really satisfy those requirements. Let's see a little example. So let's say that I want to join those 4 tables with the join order from the left to the right. And if I use traditional join algorithms, then I would start by analyzing the leftmost table. For instance, I would scan it and perhaps build some hash table for probing. Then I would scan the second table and I would join the two, thereby generating an intermediate join result. After that, I might start by analyzing the third table, and perhaps at this time our current micro episode ends. So the problem now is that I haven't started with the last join yet, and I cannot tell anything about the cost of that last join. Perhaps the first 2 joins were relatively cheap, but the last join will be very expensive. As long as I don't know anything about the last join, I cannot say anything about the overall quality of that join order. So that means I don't really have reliable early quality feedback for the current join order. Now, the other problem is if I switch from this join order to a different join order, what do I do with the intermediate join result that I have already generated? Because a different join order might actually use different intermediate results, so I can potentially not reuse it. One possibility is that I simply discard this intermediate result once I switch to a different join order. But the problem then is that I would have to regenerate it if I select the same join order again later. And that means that I have relatively high overheads for switching between join orders. A different possibility would be that I try to back up that intermediate result. Maybe I write it to disk, but it also creates overheads. And it means that I have to maintain a lot of execution state for each join order that I'm currently considering. And that does not satisfy the third requirement. So instead of that approach, we have designed a specialized multi-way join algorithm. It's a depth-first join, and I'm going to illustrate how it works by this little example. Now, the depth-first join starts with the leftmost table in join order, and it selects the first tuple there. Then it immediately switches to the next table in join order, and here it retrieves the first matching tuple, which means the first tuple that satisfies all applicable join predicates with the currently selected tuple in the first table. Now it advances to the third table, and again it selects the first matching tuple, meaning the first tuple that satisfies all applicable join predicates given the currently selected tuples in the first and in the second table. So in order to find matching tuples in a table, we can use the usual mechanisms such as indexes, of course. Now, here we have selected tuples in the first 3 tables. Now we immediately advance to the last table in join order, and we select the first matching tuple there. And now this combination of tuples currently selected in the different tables, that forms a first join result tuple. So I can add that to my result set as a result fragment. Now I advance to the next tuple in the last table, and I get another result. And after I have treated all matching tuples in the last table, I backtrack and go back to the third table in join order and continue with that one. And now I select the next matching tuple in this table. And at this point, let's assume that our micro episode ends. Now, why is this a good idea? So first of all, the execution state that I have here is entirely defined by the tuple that is currently selected in each of those tables. So this is all that I need in order to suspend and resume the execution of this join order without doing redundant work. That means that the execution state, basically one single record ID for each of those base tables, is relatively small, which is one of the things that we want. Now, the other thing is that if I switch from this join order to another join order, the only thing that I have to do in order to restore state for the other join order is that I reset those counters for all my joined tables, which can be done again very efficiently with a complexity proportional to the number of input tables. And that means that also the overhead for switching between different join orders is very reasonable. Now let's see how we can get quick quality feedback, which we need in order to quickly converge to good join orders. Now, the main idea here is to measure the query evaluation progress per time unit and to use this as a sample of the quality of a join order. And there's multiple metrics according to which I can measure query evaluation progress. I'm going to discuss 2 metrics in the following. On a high level, one possibility is to measure the rate at which join result tuples are generated. Another possibility is to measure the percentage of the space of potential join outputs that I searched during a given episode. And I'm going to make this more concrete in a minute. So let's first discuss about the first possibility, the first metric, which is a little bit more intuitive. It is based on measuring the rate at which different join orders produce result tuples. So here in this example figure, I'm comparing a blue and a green join order that process the same query. And as you see, the green join order terminates faster, so that's probably the join order that we want to converge to. On the y-axis, I measure the number of join result tuples that are generated for each specific episode. And as you see, the number of result tuples per micro episode, it varies over time. But if I count together the total number of result tuples generated over the entire execution, which corresponds to the area under those curves here, then I must find that both join orders generate the same total number of tuples because they generate the same query result. And that means that if I take this total number of tuples and divide it by the number of episodes required for execution, then I essentially get a higher value if the join order needs less episodes in order to execute. So this means that this is a metric by which I can, at least in average, identify better join orders and distinguish them from worse join orders. A join order is good if it produces join result tuples at a high rate. Now, that is intuitive, but it is a problem, because what happens if the join result is very sparse? In the extreme case, the join result might even be empty, so no join order generates any result tuples. And in this case, this metric doesn't give me any information about the quality of a join order. So I definitely want to complement at least this metric by a different metric. So we will see a second metric now, which does not have this problem. Now, the main idea behind this second metric is to look at the percentage of the space of possible join outputs that we search during an episode. Now, let's make that a little bit more concrete. We know in advance that the join result is a subset from the space of the Cartesian product between different joined tables. So I can calculate reward based on the percentage of this Cartesian product space that I search during one episode. And by searching it during an episode, I mean either generating all associated join result tuples or concluding that no join result tuples exist in this subspace. And that is the difference to the first metric. The first metric only rewards join tuples generated. So we are dependent on the selectivity of the join predicates. The second metric also rewards us for finding out that there is no result tuples in one specific subspace of the space of all possible join results. Now let's make this even more concrete by a little example. So let's say at the start of a micro episode, I have currently selected the tuples in the 4 tables that I have marked in blue here. During the episode, I advance by 2 tuples in the first table in join order and in the third table in join order. So let's see which percentage of the join output stays this covers. Now, first of all, let's only consider the advancement in the first table in join order here. Now, our depth first join algorithm has the property that it advances from one tuple to the next in the first table in join order only after it has completely searched the space of possible join outputs that use the current tuple. So after it has added all join result tuples that can be formed with the current tuple in the first table in join order. So if I advance by 2 tuples, it implicitly means that I have searched this part of the space of potential join outputs, consisting of the Cartesian product of the first 2 tuples in the first table in join order and all tuples in all later tables in join order. And if I make the calculation, that covers 2 divided by 5, meaning 40% of the potential output space. And that is only the advance in the first table. Now I'm also considering the advance in the third table in join order. If I advance by 2 tuples here, it means that for the currently selected tuples in the first and in the second table in join order, I have searched the output space formed by combining the 2 tuples in the third table with all possible tuples in the last table. And if I make the calculations again, that covers 1 out of 5 tuples in the first table, multiplied by 1 out of 5 tuples in the second table, multiplied by 2 out of 5 tuples in the third table, multiplied by all 100% of tuples in the last table. And that accounts for another 1.6%. So in total, the area that I have searched is 41.6% of the space of potential join outputs. Now, this metric is independent of the selectivity of the join predicates. And in order to finish, I know that any join order has to cover 100% of the space of possible join outputs. And that means if I calculate the average coverage per episode, I would divide 100% coverage, the same for all join orders, by the number of episodes required by one specific join order. And by maximizing this average, I thereby know that I minimize the number of episodes that a join order requires, which is proportional to execution time. So this metric as well allows me to identify, at least in average, better join orders. So I have 2 metrics that generally allow me to recognize good join orders earlier. I can use them as follows. If I try one join order for one episode, And I calculate reward based on one of those two metrics or a combination of those metrics. Then I get some distribution over possible reward values. It will vary across different episodes, even for the same join order. But I do know that the join order with the highest mean reward over the entire execution time at the same time corresponds to the best join order. Now, the challenge is that my reward per episode might vary over time. So there is some variance, which means that I cannot be absolutely sure about the true quality of a join order after trying it just for a few episodes, because perhaps what I have seen so far might not have been representative. So we need a mechanism that deals with this uncertainty about the quality of join orders in a principled manner. And fortunately, the UCT algorithm or other algorithms from the area of reinforcement learning provides us with just such a mechanism, and it guarantees that it will over time converge to those actions with the highest mean reward. And in our case, that means to those join orders with the highest execution progress per time unit. So we are converging to the fastest join orders. Now that concludes our wish list with some specialized multi-way join algorithm and a couple of scenario-specific metrics. This thereby gives us a mechanism to converge to better join orders. But we don't only want to find out about good join orders, we actually also want to finish executing our current query while converging to a good join order. And in order to make this work, we have to take care of a few issues. We first of all have to make sure that if we stitch together the result fragments from different episodes, meaning from potentially different join orders, we get a correct query result. And at the same time, we want to avoid having multiple join orders regenerate the same result tuples, because that creates redundant work across different join orders, and that means performance overheads. So I'm going to first address the first point, and afterwards I'm going to talk about the second point. Now, when it comes to correctness, if we want to make sure that we have all the required join result tuples, then we have to make sure that at least one join order covers 100% of the join output space. At that point, I can be sure that each join result tuple appears at least once in my result set. But I also have to make sure that the multiplicity of my result tuples is not higher than would be correct, because different join orders might regenerate the same result tuples. And in order to ensure that, I will have to track the way in which those result tuples are generated, as I will illustrate by a little example in the following. So let's say that I want to join those three tables R, S, and T here, and I have a currently selected join order that is running. It might first generate this result tuple here, 2, 1, 5. Then it might generate a second result tuple, 2, 1, 5 as well. But here we're talking about back semantics, so having the same values multiple times in the join result, that is okay and necessary. Now, however, I switch to a different join order, which starts processing from scratch again. So that join order might also select one of those result tuples again. So now I have 3 times the same join result tuple, but only the third tuple is redundant. The first 2 tuples, they belong to a correct join result. Now, in order to find out that the third tuple is redundant, it is insufficient to only look at the join result tuples themselves, because by doing so, I cannot distinguish whether those join result tuples are actually redundant or not. In order to verify which of those join result tuples are redundant, I can look at the way in which those join result tuples have been generated at the lineage. I can look at the record IDs of the tuples in the base tables that have been used in order to generate those join result tuples. Now, in this case, if I look at the lineage, for instance, for the blue join result tuple. I see it has been generated by combining the tuple with record ID 0 from table R with the tuple with record ID 1 from table S and the tuple with record ID 1 from table T as well. And with that lineage, it becomes kind of obvious that the first and the third join result tuples are redundant. So with this lineage, I can make sure that the multiplicity of my join result tuples is not higher than what appears in a correct join result. All right. Now, another point is that I want to avoid generating the same result tuples across different join orders in order to avoid redundant work. And the main idea here is that we fast forward over tuple combinations for a specific join order if they have already been processed according to a second join order. So I want to transfer execution progress across different join orders. Now I'm going to illustrate how we can do that for a simple example. Let's say that we just want to join two tables, R and S. Then I can represent the space of possible outputs by a two-dimensional plot. I can, for instance, process the join order R joined with S, which means that I iterate over tuples in R, and then I use, for instance, an index on the join column in order to retrieve matching tuples in S. So if I follow this join order, I could represent evaluation progress with this blue area over here. For one fixed tuple of R, I'm iterating over tuples of S, and I'm processing matching tuples, and I'm doing this until the current micro episode ends. Now at this point, there will be a couple of tuples from R that I have entirely joined with all possible tuples in S, and thereby we know that other join orders don't need to reconsider those first few tuples in R. We also call this the offset of R. So if I switch to another join order, in this simple example, the only possibility is the other way around, S joined with R. So we are iterating over tuples in S, and then we find matching tuples in R. So this means that when doing that for a fixed tuple in S, we can jump over the offset of R and immediately start with those tuples from R that haven't been fully processed yet. So here I am doing this. So here for a first tuple from S, I have processed all the matching tuples in R, but without reconsidering the offset of R. I'm doing this for a second tuple in S and for a third one. And now if I terminate the current episode and perhaps switch to the first join order again, I can again calculate which tuples from S have been fully joined with all interesting tuples from R, and I don't need to reconsider those tuples as well. Now, this is how we can minimize redundant work for one join, but let's see how we can generalize this to multiple joins. Now, let's say I have a larger join order R, S, T, and U. So for the first table R in the join order, I can definitely store the offset as before. Now, for the second table in join order, I can additionally store how many tuples we have already processed given the currently selected tuple in R, because our depth first join algorithm will first process all the tuples in S for the currently selected tuple in R. And similarly for T, we can store how many tuples we have already processed given the currently selected tuple combination in R and S, and we can proceed similarly for U. Now, in order to share that progress between different join orders, we can store it in a tree data structure, which contains nodes associated with different join order prefixes, and we can store the corresponding offset in those nodes. So if I have, for instance, a join order RSTU here marked up in orange, and have another join order marked up in green, which is RSUT. And perhaps I'm currently switching back and forth a lot between those two join orders because I'm not yet sure which one of them is better. Then those join orders can easily share all progress that have been achieved in their common prefix. And that actually makes a big difference in practice because the UCT algorithm typically converges relatively quickly to fixed tables for the first few positions in a join order, but it takes a bit longer to converge in the last tables, in the last positions of the join order. And with this mechanism, as long as join orders share at least the same prefix, which they often do, they can share most of the evaluation progress that they make, so we minimize redundant work. Now, so far, I have talked about sequential execution, but of course, we need to think about parallel execution as well. For the moment, we focus on parallel in-memory execution on multi-core systems, and we have some ongoing work in that space. Now, our approach essentially merges query optimization and query execution. So a priori, we have multiple possibilities about how to partition work across parallel workers. We can, for instance, decide to partition the space of possible join orders and to assign different partitions to different worker threads. Or we could decide to break up the connection between query optimization and query execution and assign certain threads exclusively to optimization tasks and certain threads exclusively to execution tasks. Or, of course, we can partition the data that we are operating on and assign different threads to different data partitions. And it turns out that for many benchmarks, this last approach works best. So a little word on how we do this. It's a relatively high-level description. So let's again say that we want to join those 4 tables. The way we partition the data is that we select one table as the so-called split table, which will be partitioned over different tasks. Now, with our depth-first join algorithm, we exploit the split table as follows. If we have multiple threads, they follow the traditional depth-first join algorithm, like in the sequential version, until they arrive at the split table. And then starting from the split table, each thread is assigned to a disjunctive subset of tuples in that table. So starting from the split table, they will diverge in which tuples they consider. And if we take the union of the results produced by different threads, we obtain also a complete query result. Now, you might be wondering why we don't always select the leftmost table as split table, because, of course, the different threads have some redundant work before reaching the split table. And indeed, as long as data is uniform, that turns out to be the best approach. But if data is skewed, it might happen that by partitioning the leftmost table, we actually assign some heavy hitter and all associated work to one single thread, which defeats the purpose of parallelization if it goes badly. And therefore, we actually don't fix the split table upfront, but we also adapt the split table over time based on runtime feedback, similar to how we select the join order. So our goal is to converge to an optimal combination of a split table and a join order, and that turns out to work quite well in practice. The implementation of SkinnerDB is publicly available. We re-implemented a new prototype from scratch after our Sigma 2019 paper, and that new prototype is multiple times faster than the original. So far, I have been mostly talking about the join phase because this is where the primary technical contribution of our approach is. But the join phase is only one out of multiple query evaluation stages. For a new query, we start by first evaluating all unary predicates in order to obtain filtered tables that we join. The next step is that for those filtered tables, we create indices on the join columns in order to support all possible join orders, because we want to make the join ordering decision during the join phase. And of course, like creating indexes in order to support multiple join orders instead of one join order creates some overheads that traditional systems don't have. But as I will show in a minute, those overheads turn out to be quite reasonable. And after the join phase, we still have to do things like grouping and aggregation in order to generate the final query result. So this is the process which we perform for one simple query. If our input query has a subqueries, then we first have an nesting stage in order to decompose one complex query into a sequence of simple queries. Now, we also, by the way, call everything that happens before the join phase pre-processing and everything that happens after the join phase post-processing in the following experimental results. Now, the current prototype focuses on processing analytical queries, not transaction processing. We focus on in-memory processing and use a column store architecture. We use features like string compression and runtime code generation, which are fairly standard, but still it is interesting to show that those features can be used in the context of intra-query learning as well. The most distinguishing feature of SkinnerDB compared to a more traditional database system is, of course, the fact that we don't maintain any data statistics, we don't use any cardinality models, and we don't use any cost models, but we make all those planning decisions at runtime with reinforcement learning instead. Now I'm going to show a little extract from our experimental results. You can find more experimental results with more baselines and more benchmarks in our papers. But what I'm going to show in the following shows somewhat representative picture. Now here you see some comparison between SkinnerDB and MongoDB, a state-of-the-art analytical database processing system. We also compare against Eddies, which is another adaptive processing strategy, but focused more on stream processing. We compare on different benchmarks that we classify according to how difficult they are from the query optimizer perspective. In particular, we take into account how difficult it is to estimate cardinality, because this is in practice what makes query optimization hard. If it is difficult to predict the cardinality of intermediate results before query execution. So on the one side of the spectrum, we have TPCH here with scaling factor 10. Here we operate on uniform data, and that makes cardinality prediction fairly easy. Now, somewhere in the middle, we have things like the join order benchmark, which operates on real data, the International Movie Database. And that data is not perfectly uniform. It's somewhat skewed, but not too skewed either. And then on the other side of the spectrum, we have things like JCCH. That benchmark reuses the query templates and database schema from TPCH, but it is based on very skewed, artificially generated data, and it makes it extremely hard to predict cardinality. And as you see here, the relative performance between those baselines depends a lot on how difficult query optimization is. When it comes, for instance, to TPCH, then clearly SkinnerDB compared to MongoDB, for instance, has overheads due to all the learning and join order switching. On the other side, if you consider benchmarks where query optimization is not quite trivial, like the join order benchmark, then SkinnerDB is somewhat on the same level, such as MongoDB. And finally, if you consider benchmarks such as JCCH, where query optimization is really hard and it's easy to make bad decision for performance, then SkinnerDB significantly outperforms all the other baselines. So there's a trade-off here. It depends on how difficult query optimization is. But even for something like TPCH, our performance is somewhat in the same ballpark, even if somewhat worse compared to MongoDB. Now, those performance differences are explained by two opposing effects that we can analyze in a little bit more detail for the join order benchmark. Here on the left-hand side, you see a plot giving the processing overheads per intermediate result tuple for SkinnerDB and for MongoDB. And here you see that SkinnerDB clearly has higher per tuple processing overheads due to things like learning and join order switching and so on. Now, on the other side, on the right-hand side, you see how many intermediate result tuples were generated when processing the entire benchmark. And that is only a function of the quality of the join orders that are selected. And here it turns out that SkinnerDB selects join orders that require significantly less intermediate result tuples. So those two effects somewhat outbalance themselves for the join order benchmark. We generate less intermediate result tuples, but we have higher processing overheads per intermediate result tuples. So if query optimization is very easy, probably our approach doesn't pay off. But if query optimization is somewhat moderately or very difficult, then you might want to consider it. A nice property about the performance of SkinnerDB is that it is very robust to query reformulations. For instance, if I replace all the predicates in the join order benchmark by semantically equivalent user-defined predicates, that can actually make a big performance difference for systems that use static query planning, because it might trigger different and suboptimal join order choices. While on the other side, for SkinnerDB, the way in which the query is formulated doesn't make any difference whatsoever, because we treat all predicates by default as black boxes and make decisions only based on performance properties that we observe at runtime. So reformulating the query doesn't change our join ordering decisions. And even if we don't use user-defined functions, which might be particularly hard, if we just reformulate an equality predicate to a semantically equivalent like predicate or in predicate, then that already can trigger suboptimal join ordering decisions. But for SkinnerDB, those things don't make a difference. When breaking down execution time according to those different query evaluation stages that I mentioned before, the breakdown depends on the benchmark at hand. For instance, for TPCH, we have a relatively expensive post-processing phase due to all the aggregates and the grouping, while for the join order benchmark, that is not really the case. Pre-processing is always a non-negligible component of our execution time. And there you see that time required for creating indexes on the join columns to support all possible join orders, that this always accounts for a non-negligible percentage of the pre-processing time. So here we pay some overheads, but altogether it is somewhat reasonable. Joins are always expensive. So in the following, I'm going to discuss a couple of different factors which impact the processing time for the joins in particular. For instance, we can try to select different reinforcement learning algorithms for the join phase. Our initial version used the UCT algorithm already. Now we have recently tried some other reinforcement learning algorithms, for instance, the BRIE algorithm, which has been proposed more recently. In our benchmarks, it can actually not quite match the performance of the UCT algorithm, and selecting join orders randomly, that clearly doesn't work very well. So it seems that the UCT algorithm is actually a good choice for this problem. We also tried out different reward functions. In our initial version, we had a reward function that was based on which percentage of the join output space we cover per episode. Now we found that by combining that with the number of join result tuples that are produced per episode actually yields slightly better results, as you see in this figure. We tried out different parallelization methods, and here you see among the alternatives partitioning the data by split tables, as I quickly discussed before, yields the best performance. But it is crucial to select the right split table. Simple heuristics such as always selecting the first table in join order, always selecting the largest table in join order, they don't work so well. But our approach based on selecting the split table using runtime statistics, that turns out to work quite well in practice. We also tried the intra-query learning approach on top of traditional execution engines. Here I'm showing experimental results for Postgres. You can find more experiments on this in the paper. So here we are essentially forcing the Postgres query execution engine to execute join orders for short periods of time, and those joint orders are selected via reinforcement learning again. If we compare the performance we get on a joint order benchmark against the performance we get with a well-tuned setup of Postgres, then clearly using the original Postgres version turns out to be more efficient. And if I say a good setup for Postgres, then in the context of the joint order benchmark means in particular that we want to deactivate nested loops join. That is an optimization that has already been pointed out in the paper in which that benchmark has been proposed. Because if we have nested loop joins activated, then the Postgres optimizer may often mispredict cardinality and choose nested loop joins over hash joins in situations where they are significantly less efficient than the corresponding hash join. And that leads to highly suboptimal performance. So it is a very easy tuning change to make. But of course, you first have to know which tuning change you want to make in order to get the best performance out of that benchmark. And in practice, that would require a little bit of experimenting and quite some expertise. So if we compare our intra-query learning approach on top of Postgres against a non-tuned version of Postgres out of the box for that benchmark, basically, then actually it becomes interesting to use our intra-query learning approach instead. But in any case, using our specialized execution engine is by many orders of magnitude faster than trying to instantiate this progress on top of existing database engines. Now, in ongoing work, we are currently looking at how to improve the parallel execution further. We're also expanding the scope for learning from join order decisions to other query planning decisions. And together with Dan Oltino from Oxford, I'm also currently looking at how we can translate this approach to the domain of worst case optimal join algorithms. Before I conclude, I want to thank the SkinnerDB team. SkinnerDB was actually perhaps the first project that I started after coming freshly to Cornell. So the first version was actually implemented by some amazing undergrads, Sama Mosley and Joseph Antonakakis. And later we had some amazing PhD student working on the project. Currently, that is mostly Jingxiong Wang. And the parallelization variant is currently mostly worked on by Zion Wei. All right. So that was the SkinnerDB system using a combination of adaptive processing and reinforcement learning that we call intra-query learning. On the downside, we do have to pay with some overheads for queries where query optimization is actually easy. So there, using our approach does not pay off. On the other side, if it is hard to find good query plans, then we perform significantly better than baselines. And one nice property of our approach is that performance is very robust to the way in which the query is formulated. And that is kind of the basic promise behind declarative query interfaces, that performance does not depend on the way in which the query is formulated. With intra-query learning, we come pretty close to this ideal, while with static query planning, it is actually quite hard to achieve. So thank you very much for your attention. And now I look forward to your questions. If you have questions after this talk, please don't hesitate to reach out to me at itrama@cornell.edu, or in order to see other projects that are currently going on in our lab, please have a look at my website, www.itrama.org. Thanks for your attention.
So thank you, Professor Tremmer, for the great talk.
Thank you.
Let's see if there are questions from the audience. We can still have some time for a few questions. Yeah, I think Christian raises his hand.
Yeah, just a really simple question. What do you assume about the data layout? Maybe you've said it and I missed it, but do you assume fast random access to tuples? Like everything has to be indexed in memory, right? Otherwise, I don't see how this would work.
Okay, great point. So we are currently focusing on in-memory data processing. And indeed, when having high random access overheads you would have to pay for the random switching. We don't assume that data is indexed beforehand. We actually create all the join indexes that we need during our pre-processing phase at runtime. So the time for creating those join indexes is already integrated in those experimental result times that I have shown. What makes this cheaper is that we apply unary predicates first. So we create those join indexes only for those tables that remain, but for those tuples that remain after applying unary predicates. But there is some overhead associated with enabling us to efficiently try out all the different join orders. So we do indeed create join indexes in order to support all possible join orders in the join phase.
Quick follow-up question on that. Do you assume anything about data order being randomized?
So, I mean, if that wasn't the case, then we could shuffle the data. If data is sorted, you would probably want to either introduce some additional layer that maps specific positions in the depth first join algorithm to previously randomly selected positions in the base tables, or otherwise you could just shuffle the data before starting execution. So if you have sort order that might lead to something which is a non-stationary reward distribution, because you will have a change over time, and maybe one join order, you might not get representative quality samples for the join order if there is a sort order present. So you would want to introduce some mechanism to randomize the positions of those tuples if you have an order.
Got it. Thank you.
Sure. Great questions.
I think Johannes has a question.
Yeah, thanks, Matt. A really interesting talk. So I didn't know about this interesting processing strategy. I mean, I think that's that's sort of very interesting, and I'm wondering how important is that? Because I mean, maybe you could create an index. Is it because the index construction time would otherwise be very significant? And what is the impact of all of this?
Okay. So the question is about the overheads of those index creations. And do I understand that right? That the question is whether we can also execute this on top of traditional engines?
Well, and especially it seems like you have to apply all the unary predicates beforehand, right? And what if some of these are, and it seems like the way you apply them is through scans, or how do you apply the unary predicates? Okay,
great question. Yes. So we apply those unary predicates at runtime, of course, and indeed by scanning the base tables completely. If we have already an index present in order to quickly evaluate equality predicates, for instance, we are also able to exploit that index. So we exploit whatever indexes we have already, and then we create all the indexes that we still need. So in the paper, we have some experiments about the different indexing configurations. So in those experimental results, I did not assume that any indexes were previously present. So in that case, you have to indeed scan through the base tables in order to evaluate the unary predicates.
Okay, thanks.
And preprocessing is a non-negligible component of our total runtime. So typically for the benchmarks, it accounts for something between 30 and 40% of total processing time. So it can be a significant overhead.
Great, thank you.
Sergeant.
Yeah, so a simple question, which is that you gave some experimental results on your performance of your system. So one thing is the experiments that you did with Postgres, just seeing that the same join order, what it does. Did you try it with like SQL Server or any other database? That's one part. The second part is for the hardware for which you reported results. How many, because you kind of create a bunch of structures, right, to do bookkeeping. I'm curious, how many concurrent analytical queries did you support? What was your degree of concurrency on that piece of hardware, right? Because I just want to see what is your overhead, because, I can, if I just execute one query on the box, that's different from how many working sets and the memory you are using, and what's the slowdown so how much concurrency did you support? Did you do the experience?
Okay, great questions. So about the first question, we do have some experiments with other database systems where we try to instantiate the intra-query learning strategy on top of those systems. We tried MongoDB and also a commercial database system. So I think that's also one of the extensions that we're thinking about. So far, we're focused on the specialized execution engine, but I also think that you could go further with the approach on top of existing execution engines. And with regards to the second question in terms of concurrency, right now, we only consider single user scenarios. So we process one single query, but the number of threads that process the query together, we tried with up to 30 threads currently.
Yeah, I mean, I think it's important to see how many you can support on such a box, just to understand, because I can blow up my use of, resources a lot within a query, and there's a trade-off, right? That how many concurrency I can do. So
that is true. So you're concerned about the main memory consumption for those data structures?
Yeah.
Yes.
Yeah.
Okay. Yeah. So, I mean, in terms of data structures, we also have some experiments on the main memory consumption in the paper. In fact, our prototype that we evaluated for Sigmod was significantly more main memory hungry. At this point, in order to run the join order benchmark, for instance, we consume 16 gigabytes of main memory. So the biggest data structures that we need to store is actually the filtered tables after pre-processing. We also have some data structures about storing statistics for the UCT algorithm, for instance, or in particular storing the offsets for the different join orders in that tree data structure. Among the two, the latter one turns out to have more space consumption, but it is in space consumption, it's significantly lower than the space we consume for storing those tables after applying unary predicates and for storing.
So the other thing is, what was not explicit in your optimization criteria was, are you optimizing for the first k tuples or the end of the query processing? Like, for example, in traditional engines, I can pick a different plan based on, for example, whether I want the first k queries or the latency to the first query versus the end-to-end job throughput, right? So
latency of the first query.
So, for example, I can just let me give you a stupid example. Let's say I do a nested query, right? I mean, just to say, maybe the first tuple will come out first, but it will take me a long time to finish the query, right?
So you're talking about one query where I have different nested queries within the same query.
Yeah, well, one, I might use a hash join, for example, and I might, the query might end much, faster, end of the query. The other is the first tuple that I get is first.
So you're talking about like situations where we have for one query plan some startup overheads where we need to invest time to create a hash table, for instance. So it would take longer until result tuples start coming out. Yeah. Does it refer to that? Okay, very good. So that's a great question. We kind of try to take out anything which is startup overheads and put it into the pre-processing phase. So in the pre-processing phase, we create hash indexes on the join columns, which means that we can very quickly identify matching tuples for equality joins, so that at runtime, we essentially don't have any operations that have, so in the join phase. When I say runtime, I more precisely mean the join phase. So in the join phase, we don't have any operations with high start. Creating one hash table on one of the base tables. We would create hash tables on all of the base tables after predicates in order to support all possible join orders. So there's a trade-off here. So we invest that additional time during pre-processing exactly for the reason that you mentioned, exactly such that we don't need to take into account startup costs anymore during the join phase.
Okay.
Yeah,
Thanks.
that's a great point.
I think Anshuman has a question, right?
Yeah.
Go ahead.
Thanks for the very good talk. It was very clear to understand some of the things which, I didn't understand earlier. Two-part question. One is that you presented the amount of time spent on pre-processing and the join phase and other things. Do you expect it to change significantly as we go to larger scales, such that 100 GB TPCH or something? And the second question, which is related to the reinforcement learning part, is that you were pointing out about 10,000 episodes per second or something. So the question is that, is it sensitive to that choice, or there is a good number which worked across all three benchmark evaluations?
Right. So we used, so great questions. So first of all, about how the breakdown into different phases changes when we increase the data size. So the thing is that for pre-processing and for post-processing, in principle, the time should scale linearly in the input query size. I mean, for instance, applying unary predicates, it means I can just iterate over those tables. While for the join phase, that is not necessarily the case. So I would assume that if you keep increasing data, then probably the join phase becomes more dominant, as long as the selectivity of the unary predicates remains the same, for instance. And when it comes,
really depends on the intermediate join sizes, right?
True.
It depends on the filters, the correlation between tables.
True. It depends on the relationship between the intermediate and final result sizes and the base table sizes. I agree with that. So it would depend a bit on query properties. But if we talk, for instance, about those, I mean, the thing is that the overheads that we have compared to a traditional query evaluation, when it comes, for instance, to applying, generating those join indices and so on. So that should scale relatively gracefully in each case in the input data size. And then how the breakdown evolves, that depends indeed also on the ratio of the selectivities of the join predicates. For the second question, you asked about which number of episodes per second is a good idea. So we use the same settings for all three benchmarks. We are actually fixing the number of computational steps in a join algorithm to 500 steps per micro episode. So that is relatively fast. And that worked well across all those different benchmarks. I mean, the thing is this, you want to give the reinforcement learning algorithm as much tries as possible in order to figure out good join order. So a more fine-grained partitioning of time into micro episodes is better for the reinforcement learning algorithm. You just have to pay attention that the overheads are related to the reinforcement learning algorithm, which is, for instance, traversing this UCT search tree and expanding it by a limited number of nodes per episode and updating the statistic, that this does not become dominant compared to the time for doing the actual join. So with 500 computational steps, we found that the overhead of the UCT learning are somewhat dominated by the join time, and therefore it makes sense to use that setting. I mean, in general, from the reinforcement learning perspective, the more micro episodes per time unit, the better. But at some point, the overheads related to learning become dominant, and you want to avoid that.
So just quickly, it should also depend on the planned switching overheads, right?
Yes, okay, the plan switching overheads as well. So
and plan switching overhead depends on what? I couldn't get that part from the presentation. That what does the plan switching overhead depend on?
So the plan switching overhead, I mean, the only thing I need to do in order to switch to a different plan is actually to, I mean, after I have selected a join order, I want to look up what is the basically the tuple combination from which that join order should start again. And then I simply reset counters for each of the base tables to whatever I retrieve from the progress tracker tree data structure. So the complexity of that is proportional to the number of input tables. I just need to reset one counter for each of those input tables, and then I can just restart the join algorithm with the new join order and from the current counters.
Okay, thank you.
Sure, great questions.
Yes. Hi, Emmanuel. So I have a question about how the performance of SkinnerDB sort of grows with the number of joins. So as you already mentioned, the number of join orders grows exponentially with the number of joins. Now assume, but that doesn't mean the query execution time grows exponentially, right? So assume on the same database you have two queries, one with a larger number of joins, one with smaller number of joins. By limiting the overhead of the join phase, the join exploration phase, it seems to me for the query with a larger number of joins, the percent of join orders that has been explored by the reinforcement learning is sort of smaller than the one with smaller number of joins given the bounded join overhead. So have you observed any difference in terms of performance for queries with a larger number of joins and smaller number of joins?
Okay, that is a great question. Right. So if you have a larger space of join orders to explore, then in principle, it could take longer to find the appropriate join order. Now, for the benchmarks that we have tried, the overhead of finding good join orders is actually negligible compared to the total execution time. So we made some experiments which are in the paper where we, for instance, we fix the optimal join order beforehand. So we don't do any learning, and we compare the time that we incur there against the time that we have with intra-query learning. And the gap between the two is actually fairly small, which means that the overheads of converging to good join orders are fairly negligible. During parallelization, we also tried an approach which tries to divide the join order space across different threads. And for the benchmarks that we tried, it didn't work very well because the overheads of finding a good join order are again rather negligible. Now, one of the nice things about this UCT algorithm is that we structure the search space in a hierarchy as a tree, which means that even if you only get the first couple of tables right, then you might already have a join order that works reasonably well. And at the same time, it tells you something not only about that specific join order, but it will motivate the UCT algorithm to search more join orders that are located within the same subtree of the search tree. So while I agree with the point. So in principle, if you extend the space of join orders more and more, and if those good join orders are extremely sparse, then at some point it might be difficult to identify them, depending on how much data you have to process. So the learning approach is, of course, happy if it has more data that it can use in order to explore the join order space. And I guess in principle, there must be some kind of cases where you have an extreme number of possible join orders and extremely little data to process, in which case exploration might become a significant component. But for those benchmarks that we tried, and I mean, we see that for TPCH and JCCH, we also used some small scaling factors. In the Sigmod paper, we tried the scaling factor 1, for instance. So already in that scenario, the join order exploration overheads are actually quite negligible. So it finds the right join order fast. But I agree that in principle, if you keep extending the space of possible join orders, it might become difficult at some point, but we haven't really encountered that in our benchmarks.
Thank you.
Great question.
So I think Johannes has one more question.
Yeah,
Oh, yeah,
maybe one other question. So, you know, it's really interesting. You do a lot of work right now within a given query, right? But the database system doesn't have a single query, right? And I think doing it within a query, it means that in some sense you don't have the problem if updates are happening, right?
Correct.
That everything gets outdated, but I mean, it also has lots of disadvantages probably. So have you thought about how I would sort of do this over the lifetime of a system?
Over the lifetime of a system. So, I mean, I agree that in a way, the approach that we are following here for the moment, it's quite extreme because we really assume zero knowledge before the query comes in. And I agree. I mean, like the advantage would be that we can execute immediately on freshly loaded data. We don't need any existing statistics. Also, if you introduce, for instance, a new user-defined function that the system has never seen before, it doesn't matter for us. We can anyway get our guarantees. So when using this over the lifetime of a system, so
well, I was more thinking about not throwing away what you've learned from previous queries, right? Yeah.
Okay, that's a great point. We are actually currently thinking about whether there's ways to combine the two things. I mean, one could think of approaches that, for instance, use experience gains from prior queries as prior or as a heuristic, and then as query processing proceeds, slowly essentially reduce the weight that those prior experiences take and rely more on experiences that have been gathered for the currently running queries. So that's a great point. I think it would be possible to combine those two. And perhaps, I mean, even also relating to the previous point, if there's queries where the join order space is extremely large and the exploration would take a long time, one could consider using some kind of heuristics based on prior queries or some kind of other statistics in order to start execution and then to tune in more and more intra-query learning as execution proceeds. We did actually make a few experiments, which are in the Sigmund paper as well, where we tried some hybrid approaches where we mix propositions that are made by a traditional query optimizer and propositions that are made from the learning optimizer. And we switch between the two, and that can actually work sometimes better than the approach that is based on pure intra-query learning, at least when executing it on top of traditional systems. So that is a great point. I think, yes, it would make sense to combine them as well at some point.
Thank you.
Yeah. But I mean, yes. So I mean, for the current benchmarks and queries, it really turns out that those join order searching overheads are relatively small, but there might be other queries where this is not the case. Great point.
Thank you.
So Vivek, please.
Yeah, thanks, Menta. Thanks, Emmanuel. I
Awesome.
was wondering whether you ran some experiments along the following lines. So like for those queries where SkinnerDB, let's say, took longer to execute compared to, say, MonetDB, right? Mm-hmm. Now, for that, suppose you give that same amount of extra time to the MonetDB optimizer, maybe by giving it more accurate cardinality information, or maybe giving the search algorithm more time to search better plans, would the quality of the plans then be very similar? Or you think, no, there's something much more fundamental about SkinnerDB that gives it a huge leg up?
I mean, I guess the right time investment would in any case be to rather get more data statistics, because I think the main problem for instance, for the JCCH benchmark, it's not that the plan space is overly large, but it is rather that it's very hard to accurately assess the quality of a plan before executing it. So the question is how efficient you can be at collecting more samples at runtime. I mean, given the overall performance compared to MongoDB, I think it would be hard to beat that by a different approach. So, I mean, in a way, the nice thing is that in our approach, we essentially combine execution and sampling for optimizer decisions. So any other approach, I'm not sure whether it could be more efficient at collecting those samples. The nice thing is also that since we never stop learning over the execution of the entire query, we can make those formal guarantees about converging to optimal join orders. If you fix any amount of sampling that you do before query execution starts, then you cannot give the same guarantees already, because it is very hard to say in advance how much samples you want to collect, because in advance you cannot reliably predict how long the query execution takes, and you would like to take a sample that is proportional to the query evaluation time. So I think if you want to rely on samples that are collected at runtime, then this SkinnerDB approach is probably perhaps the most principled way of doing that.
Okay, thanks.
Sure.
It looks like there are no more questions. So if you have further questions, please just send emails to Professor Trummer or communicate offline. So let's thank Professor Trummer again for the great talk.
Thank you very much for the invitation.
Thank you. Great talk.
Thank you very much.
Thank you.
Thanks a lot.